So hello everyone, we are on page 5 of the handout and I'm going to discuss the 3 questions that you will find there. Question 1. We're given a cubic curve here and we want to know where on that curve is there a gradient of 27. So every time there's talk of gradient, there should be talk of the derivative. So we're going to find the derivative function of x cubed minus 1, apply the power rule to x cubed, 3, that was the power, subtract 1 from the power, that's 2, minus 1, the derivative of that is 0, okay, because this is a constant. So this is my derivative, and remember that this is the function of the slope. Okay, so if I'm looking for a slope of 27, right, what I'm really saying, put these two together, is that I want to know where does this function, which describes the slope, where is that equal to 27? So I'm going to solve this, divide by 3 on both sides, getting x squared equals 9, and then x, watch out here, is plus minus 3. So I've got 2 candidates that I need to evaluate in my function. There could be a gradient of 27 at 3 and at negative 3. So let's see what this looks like in f. If I substitute 3, I'm getting 3 cubed minus 1, that is 26. If I substitute negative 3, I'm getting negative 3 cubed minus 1, and that's negative 28. So from the first one here, I'm getting the first point, well, the x-coordinate is 3 and the y-coordinate is 26. And from this, I'm getting my second point, negative 3, negative 28. So these are my 2 answers, but because they're all a bit theoretical, I'm going to check this and show you on the graphics calculator. So I've typed in x cubed minus 1, that's my function. I'm going to get a graph of it, and I want to find the slope of the function at a particular point. My calculator can do this for particular points. So I'm choosing menu 6 here, dy by dx, and I can type in x values here. It doesn't look like it, but just type in a value, for example 3, and it appears here, enter, and it will calculate the derivative to be almost 27. That fits our question. I can repeat that process for this second point, negative 3 here, and check that that also gives a gradient of 27. Okay, and let's move on to question 2. What I suggest you actually, while you're watching, just watch the whole question, then you're going to see all the writing on the screen, then take the notes for that. I suggest that approach. So, we've given this parabola here, and so I'm going to find the derivative because the slope is involved here. Applying the power rule to x squared gives 2x, so 2ax, and bx, the derivative of that is b. I'm going to use 2 bits of information. Firstly, at the point 312, I know that the slope is 13. So this translates to the following. I'm going to substitute 3 and 12 in this information, and the slope given by that function must be equal to 13 at that place. So simply substitute 3 in here. 2a3 plus b equals to 13. That's the first information. Let's look at the second information. I also know that the point 312 is on my original curve here, is on y. And that means, well, I can substitute these coordinates in that function. That means I'm going to get 12, that's the y equals here, a times 3 squared plus bx, so b times 3. That's another equation. Let's go back to the first equation and work with that one. I'll simplify this. I'm going to get 6a plus b equals to 13. And I'll simplify this one. I'm going to get 12 equals to 9a plus 3b. Then I'm going to solve this one for b. b equals 13 minus 6a, and b equals to 4 minus 3a. So you have a pair of simultaneous equations which I have typed in here. I can graph them to see where they intersect, and second calc intersect will give me the solution to the simultaneous equation. Please do that yourselves to show that the value of a is 3 and the value of b is -5. Basically solved my question now. I'm going to do one final thing on the calculator though. Because if I substitute these values into here, I'm obtaining the function y equals 3x squared minus 5x, and it's worth checking on the graphical calculator that at this point I've got a slope of 13. Let's do that. So I've typed in my parabola in here with the values of a and b substituted. If I graph this, I'm getting a nicely parabola, and if I evaluate now dy by dx, option 6, at the point x equals to 3, I should get 13 as an answer, and I do. Okay, so I've just checked on the GDC that dy by dx for x equals to 3 gives 13 as it says in the question. Right, I suggest you copy that now. And on to question 3. So what I recommend is you type this parabola into your graphical calculator, or you use your knowledge of zeros to confirm that we are getting this red curve here. I've produced a sketch which you can copy later, okay, but what the question is asking is that we should be looking at a tangent through this point here, because that's where y equals 0, and also y equals 0 is here, okay. So if I change the color here quickly to blue, this tangent touches the parabola here, and the other tangent touches that parabola here. Let's call this tangent 1, and this is tangent 2. And both tangents meet in a point which we'll call P. That's what is being discussed here. Okay, so first of all, let's copy out the function, and let's, instead of y equals, I actually prefer when dealing with calculus to use f of x. You'll see why in a moment. Because, well, first of all, I can find the derivative like this, that using the power rule, that's going to give 6x plus 9. Right? And now I'd like to evaluate this slope function at x equals to 3. So I'm going to write slope at x equals to -3, and eventually I'll do that at 0 too, if x is -3. Okay, sorry for the interruption here. I had to rewrite this on the left to have a bit more space. So let's get going. Let's first find the slope at -3. Okay, well, I'm going to have to evaluate f prime of -3, which is 6 times -3. I substitute -3 in here, yeah? Plus 9. That equals to -9. And I'm going to do the same thing at 0. F prime of 0 equals to 6 times 0 plus 9, and that is going to be 9. So the slope of this tangent is -9. That seems to fit, and the slope of that tangent is 9, and it's also good that they're nicely symmetrical because we're talking of a parabola. I can in fact write down the equation of that tangent. That's going to be 9 equals minus 9x minus 27. Please pause the video here for a moment to figure out why I wrote this. And the equation of the second tangent is y equals 9x, much more simply. Right, now p is at the intersection of these two. Okay, so p is at intersection of tangent 1 and tangent 2. That's one way, so simply I could solve this simultaneously here to find out at what x value and y value do these two meet. Or I can simply say, through symmetry, P has x coordinate x equals -1.5. I can see that here, isn't it? If from -3 to 0, P must be somewhere here, that's -3/2. Okay, so I'm going to substitute that into T2, that seems the easiest. Okay, 9 equals 9 times -1.5, and that's -13.5. And so I am obtaining the coordinates of P as -1.5, -13.5, and I've answered the question.